In this video, we're going to take a look at quantum mechanics. This is following up on our history of the atom, where we took a look at Dalton, Thomson, Rutherford, and Bohr, and the different things that they studied to come up with their different models of the atom. Notice that the models are getting successively more complex, and we're coming to a closer understanding of the true nature of the atom in each one of these. Quantum mechanics is our current model of the atom, and the quantum mechanics model is really dependent on several different scientists. In fact, you could take a look at a poster of the physicists in the Solvay conference from somewhere around 1920, and everybody who's anybody that worked on quantum mechanics is in there. It's a pretty neat poster. It's hanging in my room if you guys want to check it out. So the quantum mechanics model has a few big breakthroughs, and one is that light is behaving as a wave, and this was described by James Maxwell in the mid-1800s. He said that all light, whether it's radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, cosmic rays, it's all just different frequencies or wavelengths of electromagnetism that consists of an electric wave that moves on one plane, we'll say the up and down plane of the paper, and a corresponding magnetic wave, and that would be coming out of the paper and going back into the paper. So it's running perpendicular to the electric wave. And you can never have one wave without the other. And Maxwell showed this with his 4 equations of electromagnetism. So this idea that light's a wave was pretty definitive in the mid-1800s, but leading up to that, people had disputed whether light was a wave or a particle for some time. Isaac Newton was convinced that light was in fact a particle. In fact, even today, we consider that light is made of photons or particles of light. So that comes about from Albert Einstein running what's called the photoelectric effect, in which he showed that light was being absorbed in very discrete packages or particles, and it was behaving as if it were a particle. And he said, look, we have to stop saying that light's either a wave with electromagnetism or a particle with a photoelectric effect, and come to the conclusion that light has wave-particle duality. Which is to say that it's neither one nor the other, it's both. You could consider light to be a wave particle, so it can behave as a wave or as a particle. So the next step is that Louis de Broglie came up with the idea that, well, maybe electrons, which we consider to be particles, are actually waves as well. So he did some experimentation and showed that electrons were in fact moving with wave motion. And then a scientist named Erwin Schrödinger came up with what's called the wave equation. And when you solve the wave equation, very much like when you solve the quadratic equation, you get several different solutions for it. Now, we can use equations in math to plot things out. We know that if you plot out the equation y equals mx plus b, you form a line. You could use an equation for a cylinder and plot out the volume of a cylinder. But when you solve the wave equation, one of the many solutions to it is this. It's a sphere. And what we consider this to be now is an orbital. So we took that word orbit that was being used in the Bohr model and changed it around and made it into an orbital. Now we would call this an S orbital. S doesn't really stand for sphere, it's just a random letter designation. And we have other letter designations that we use for different orbitals. You might say, why not use A, B, C, and D? But the reality is that not everybody in the world speaks our languages and uses our alphabet, and since scientists from all around the world were contributing to this, it's reasonable that we would use some rather random letter designations. So we could say this is an S sublevel in the in the first energy level, and this S sublevel is comprised of only one orbital. So orbitals make up sublevels. and sublevels make up energy levels. Now, no matter what kind of an orbital we have, whether it's this orbital or one of the other more complex orbital shapes, any orbital can hold 2 electrons. So 2 electrons combine to make up an orbital. An orbital can sometimes combine with other orbitals to make up a sublevel, and sublevels can sometimes combine with other sublevels to make up energy levels. Now, energy level 1 is made up of an s sublevel, and it's a singular s orbital that makes it up, so 2 electrons could fill up this space. Now, these are wave particles. So essentially, again, what we're saying is that it's not just a particle. For example, like a peanut, you could crush that peanut up and make peanut butter out of it and spread it out over whatever you want it to spread it out. Like you can spread peanut butter over a piece of bread or a bagel or whatever you want. You can make it take the shape of whatever. So the wave particle nature of the electron is that the electron is actually spreading itself out throughout this space. So we can actually fit 2 electrons within that space. Now the electrons, when they pair up, are actually pairing up with opposite magnetic fields. So how do you get a magnetic field on an electron? Well, one of the ways we can conceive of it, and this is really oversimplified because electrons are not just particles, but if you consider the electron as a particle and it's spinning, if it's spinning in one direction, the magnetic field would be oriented one way. And remember that if you move an electron, a moving electron creates a magnetic field, right? So that would account for the magnetism of it. If you spin the electron in the opposite direction, we would get the magnetic field oriented in the opposite direction. So to choose opposite words, we have used up and down. We say the electron has an up spin or a down spin. Again, the spin is probably oversimplified, but it's good enough for us to put a handle on this. And when electrons pair up, they always pair up in opposite directions of spin. All right, so after 1s, we could see that we might get some bigger energy levels. For example, energy level 2. It might have an S sublevel as well. It does have an S sublevel as well. And that would be just a bigger version of the 1s sublevel. So we'd see that it's made of one orbital, and that orbital is just larger, because as we move farther away from the nucleus, we get higher and higher energy level electrons. So this would be 2s. Now, a little bit more energy than 2s would be 2p. We don't see a p sublevel with energy level 1, but we do with energy level 2. P sublevels are made of 3 orbitals. There is a p orbital on the y-axis, there's a p orbital on the x-axis, and there's a p orbital on the z-axis. So this could be considered the 2p sublevel. Again, the x, the y, and the z-axis are each occupied by what are known as dumbbell-shaped orbitals. So if we have 3 orbitals there, and 2 electrons are per each orbital, that means we could house 6 electrons within this sublevel. This sublevel has only 1 orbital, so it could hold 2 electrons, and this sublevel has only 1 orbital, so it could hold 2 electrons. Now, there are other sublevels out there, but the orbitals that make up those sublevels are too difficult to draw, so we're not going to try to do that. So if we were to actually put this in some kind of an organizational scheme, what we would see is the diagonal rule. And this is essentially a roadmap for the quantum mechanics model. So we see that as the arrows are crossing out these different designations of energy levels and sublevels, the number of electrons that are being occupied here in the upper right-hand corner, we're filling up an atom, moving farther and farther away from the nucleus as we go, higher and higher energy positions as we go. Now, you might look at this and say it seems kind of odd that we're filling up 1s with 2 electrons, then 2s with 2 electrons, 2p with 6 electrons, and 3s with 2 electrons, 3p with 6 electrons, but then why not 3d with 10 electrons? It turns out 4s fills in with 2 electrons first. So the other sublevels I was talking about, the d sublevel has 5 orbitals. That means it holds a maximum of 10 electrons. And the f sublevel holds 7 orbitals, maximum of 14 electrons. Drawing these is somewhat not necessary, because you can see right away when you begin to try to draw an atom, you start to get shapes that are way too complex. Let's just follow along this diagonal rule. Again, the order in which electrons fill in is the order in which the arrows are crossing out these different positions. So let's do this all the way down through the first 18 electrons. So if we follow the diagonal rule, that would be 1s2, 2s2, 2p6, 3s2, 3p6. So that's 2 more is 4, 6 more is 10, 2 more is 12, 6 more is 18 electrons. Well, element number 18, argon, because it's element number 18, would have 18 protons in the nucleus, and if it's neutral, 18 electrons. So this would be known as the electron configuration for argon. The electron configuration is one of the ways that we can represent the quantum mechanics model that's expressed as this roadmap here with the diagonal rule. Now we could say, well, let's just make a drawing of it. Okay, well, let's try to do that. Let's put the axes down for reference. And we have 1s filling in with 2 electrons. Then 2s fills in with 2 electrons. Then 2p fills in with 6 electrons. Then 3s fills in with 2 electrons. Then 3p fills in with 6 electrons. And we see a pretty scribbly drawing right here. So it's not too useful when the drawing gets that packed with information. It's easier if we can kind of spread that information out, and rather than make a drawing of it, write an electron configuration. So that's the electron configuration for argon, and we can do an electron configuration for all different elements just following the diagonal rule. The problem is that as you go through the diagonal rule, you get pretty big elements, and there's a lot of counting that you have to do. Let's take a look at a few examples of electron configurations here. Let's take a look at element number 8, oxygen. So we have to account for 8 electrons here. 1s fills up with 2 electrons. Then 2s fills up with 2 electrons. Then 2p fills up. And if we put all 6 electrons maximum in there, that's too many electrons. That would be 10, and we only need 8 electrons for element number 8, oxygen. So we're only going to put a 4 there because 2 and 2 is 4, and 4 more makes 8, right? 2, 4, 4 more is 8. So these numbers in the diagonal rule are maximum numbers that fit in those particular locations. 2 electrons in the S sublevel, 2 electrons in the P sublevel, 10 electrons in the D sublevel, and 14 electrons in the F sublevel. And that's where we come up with that. But once again, that's a lot of counting. If we were going to try to do that for a really big element, something like, say, number 51, antimony, which is SB, it would look like this. 1s2, let's go ahead and follow along the diagonal rule here. 2s2, right, 1s2, 2s2, 2p6, 3s2, 3p6, following the arrow here, not to 3d10, but 4s2, and then 3d10. That's somewhat counterintuitive, but it turns out that wave particles can kind of overlap each other, so it's not that big of a deal, right? Like you could put peanut butter and then put jelly. All right, so after 3d10, 4p6, then 5s2, oops, S2, and then, let's see, 4d10, and then, now if we put 5p6 here, that's going to be too many. That's going to be 54. Right now we have 2, 4, 6 more is 10, 2 more is 12, 6 more is 18, 2 more is 20, 10 more is 30, 36, 2 more is 38, and 10 more is 48. We have 48 electrons accounted for here so far. We need to have 51, so we need to put 3 more. So after 4d10, 5p is not going to fill up all the way with 6 electrons. We're only going to put 3 electrons there. So that represents the long electron configuration of both oxygen, and Sb, antimony. Element number 8 and element number 51. But boy, that's an awful lot of work to count through the diagonal rule. There's an easier way to do it. And the easier way to do it involves the periodic table. So let me just adjust my camera here a little bit. Got a little bit of a homemade camera boom, but it's working. All right. So what we have here is a periodic table on which I have drawn black numbers here for each period. The horizontal rows are the periods on the periodic table. The vertical columns are groups. Now, Dmitry Mendeleev put the periodic table together not based on atomic theory, but rather based on the fact that elements within groups were similar properties, and elements in the periods, originally he did it by atomic mass because he didn't know, by the mass of the elements, he didn't know about atoms, but now we do it based on atomic number, not mass. So you see we have atomic number increasing as we go across the periodic table here. So it turns out that, according to the diagonal rule, there are 2 electrons that occupy an S sublevel. Well, look at this. We have 2 columns right here. All of these elements have outer electrons that end with S1, and all of these have outer electrons that end with S2. The D electrons fill in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The P electrons fill in here. 1, 2, 3, 4, 5, 6. And the F electrons fill in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you might say, well, that looks kind of weird because how come helium isn't next to hydrogen? And that's true. It is a little bit weird, and we could make that happen if we were to take the table and kind of scrunch it together so that hydrogen and helium might meet up there, or maybe roll it around in a tube so that they could meet. But if we want the periodic table to be nice and flat so that we have all squares for each one of the elements, we're going to have to realize that is going to mean we're going to have to sacrifice something here. And what we're sacrificing is a perfect fit with the diagonal rule. Another thing that you're going to see is that it looks like it's 4s, and then that should be 4d, but that's actually 3d. And it looks like 6s, and by the way, remember you have to cut the table here and put these 2 rows in here, so we'd have to slide the table over to make that happen. So just for convenience, we always cut it up and put these 2 rows down here. Looks like it should be 6s, then 6f, but it's really 6s, then 4f. And we can see that in the diagonal rule. What comes after 6s? 4f. See that? 6s, finish up here, 4f. Then 5d, 6p, 7s. 6s, 4f, 3d, 4d, 5d, 2p, 3p, 4p, 5p, 6p, 7s. If you know these benchmark positions, 1s, 2p, 3d, and 4f, you don't really need to use the diagonal rule. You can just use the diagonal rule built into the periodic table. So let's go ahead and take a look at what that would look like for the elements that we've done so far. For example, for oxygen, 1s fills up the outermost electron on hydrogen and on helium, so 1s2. Then we fill up the 3rd and 4th electrons, the outermost electron on lithium and beryllium, 2s2. Right, 1s2, 2s2. And then 2p comes next. We fill up 4 electrons to get to oxygen, 1, 2, 3, 4. That's all 8 electrons that are found around the nucleus of oxygen. Let's take a look at antimony, Sb. You can see on the periodic table, I'm not sure if that's really going to be in focus perfectly, but antimony is right here, number 51. So, see if I can focus that in there, right there, number 51. All right, so 1s2, you can follow along down here. 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5, 6, right? If this is 2p, this is 3p, 1, 2, 3, 4, 5, 6 positions. then 4s2, 3d10, 4p6, 4s2, 3d10, 4p6, 5s2. If that's 3d, this is where 4d fills in. 4d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After 4d10, 5p1, 5p2, 5p3. So that's a long electron configuration. Being able to use a periodic table allows you to do a short electron configuration. So a short electron configuration would look something like this for oxygen. We would start with the noble gas that comes before oxygen, in this case, helium. Remember, the noble gases are the gases in this far right-handmost column, and they're all red, they're gases. So we start with helium. The International Union of Pure and Applied Chemistry in Paris decides things like this, and they've decided you have to start with the noble gas. So what comes after helium? Okay, let's continue on here. Lithium does, right? That's element 2, element 3. So that's occupying energy level 2, S1 and S2. So 2s fills in both electrons, the outermost electron of lithium and beryllium, and then 2p, 1, 2, 3, 4. So really not much of a shortcut when you have a small element like oxygen. Helium represents those 2 electrons. That's called a short electron configuration. And next we're going to take a look at a short electron configuration for antimony. So here's antimony Sb. The noble gas that comes before it is Kr. If we put that Kr in brackets, we continue on from there. After Kr number 36 comes number 37, and that's filling up energy level 5, S1, S2, and then 3D, 4D10. Right? If this row is 3D, this must be 4D, and it fills up 10 electron spots. And then if that's 2p, that's 3p, 4p, 5p, fills up 1, 2, 3 spots to get to Sb antimony. So notice that the very end here looks the same. All of this is represented by the symbol Kr. So when you're doing a short electron configuration, in this example, number 51 Sb, you start with the noble gas that comes before the element, and you continue on where that noble gas left off. Now, you can somewhat use the periodic table. If Kr is 36, what comes after 36? Well, here, that's 5s2, right? 5s2, that would be 38, because 36 and 2 more is 38. And after 5s2, 4d10. Now, you might say, I'm getting lost with that. I want to use the diagonal rule. Well, let's go ahead and do that. 5s2, 4d10, 5p6, and now you just got to continue to count. 4d10 would be 10 more electrons, so 38, and 10 more is 48. And what comes after 4d10? 5p6. So we don't need all 6 electrons, because 48 and 6 would make 54. We only need 51, right? Antimony is 51 electrons. So 48 and 3 more, 5p3, would do it. So if I add 3 onto that, I get 51. So Kr is 36. This is element 36 right here. 2 more is 38, 10 more is 48, 3 more is 51. And that's how you can use the periodic table to do long and short electron configurations, and try to minimize as much as possible having to go through and count through the diagonal rule, because that's just a lot of extra work to have to do it that way. In the next video, we're going to take a look at our final way to represent the quantum mechanics model. Besides long and short electron configurations, we're going to talk about orbital diagrams.